So today we're going to finish off notes on the fundamental theorem of line integrals, and then we're going to see if we can also tackle Green's theorem. We'll see how far we get. I think we can do both. We'll see. You do not need a laptop for this. Let's do.
Can I get like 30 seconds on that?
Sure. Yes.
Are we ever going to get back on like the one section per day?
Yes.
Like half
Starting tomorrow.
Really?
If we get through these today.
It feels so weird to say doing like half of one and then like ending the day with like the next half of one.
Well, what you need to do is tell principal version no more pet fest.
Oh, I call my.
All right.
Whoa. Just get tomorrow.
So this, quiet please, the first couple of slides are really just kind of a recap. I thought at this point it was time to just recap what have we learned so far, right? So let's just kind of put it together. So one of the first things we learned about vector fields. I'm not going to show you again how to draw a vector field because I think you're all fine with that. But we also learned how to use the determinant of the matrix of partial derivatives to determine if a vector field is conservative. That was the test for whether a vector field is conservative or not. If a vector field is conservative, it means there's a potential function, and we all know how we've been working on how to find a potential function. All right. First definition of a line integral that we learned was in terms of arc length, right? So it's just an integral over a curve C of some function with respect to arc length. So when you actually convert this to a dt integral, you have ds becomes the square root of x prime squared plus y prime squared dt, and your f just gets written in terms of x of t and y of t. So you're replacing your x's and y's with functions in terms of t's. So first line integral that we learned was with respect to arc length. Couple things to notice. I don't know if you remember this or not. Arc length is the magnitude, right? It's magnitude of the speed, the magnitude of the velocity. Like you have, it's this right here, this is our definition of arc length, the square root of x prime squared plus y prime squared. That's for a little, then you have to integrate it. But anyway, so it's the same thing as the magnitude of r prime. And so ds is equal to the magnitude of r prime dt. And it's kind of a conversion formula. You can almost think of the magnitude of r prime as like the Jacobian for converting those units from s's to t's. So anyway, so it used to confuse me how we went from ds to dt, but it's because your ds is equal to the magnitude of r prime times dt. All right, line integral of a vector field. So that's traditional line integral. It's the first definition you learned. Line integral of a vector field, f dot dr, which is the same as f dot r prime dt. So, so dr is the same as r prime dt. All right. So f, if we write f as m comma n and r as x comma y, then f dot dr equals m dx plus n dy. Why? This is where I was talking to you guys yesterday, and I was saying I would show you a little bit of a conversion. So dr dt, right, that's r, dr dt is dx dt, dy dt. If you remove the dt's from the situation, you get dr equals dx dy. So if you do f dot dr, you get m dx plus n dy. So f dot dr is actually equal to m dx plus n dy. You can do the dt's, but the dt's all end up just canceling out. So it works out nicely. So anyway, so f dot dr is the same thing as f dot r prime dt, which is the same thing as the integral of m dx plus n dy. So we did one that was like this, just with x's and y's normal. Then we learned the fundamental theorem of line integrals, which says that, hey, if your vector field is conservative, then the path to get from A to B is completely irrelevant. So why not just do the simplest path possible, which means find the potential function for big F, and then evaluate the potential function from beginning point to ending point, and you end up with an equivalent value for your f dot dr. All right, so FTLI, fundamental theorem of line integral, says that if f is conservative, then the integral over curve C of m dx plus n dy is equal to the potential function f from point 1 to point 2. Remember that if f is conservative, the path taken is completely irrelevant. All you need is a starting point and ending point to use the FTLI. Okay, there's a little more before we get into problems again. So, I don't know if I can make this a little, how do I move this up? Okay. So here's the thing. If we have an f dot dr integral, then we know that if the vector field is conservative, then this integral is the same regardless of the path taken. We also know if the vector field is conservative, then this integral also equals the potential function from A to B, basically. So if we encounter an f dot dr problem, you have three options. You can actually find f dot dr, like you can do it. Do the dot product of f and r prime, and with respect to t's, and you'll be good. Or you can find a new path, right? Your r of t, say your r of t is some crazy convoluted path from point A to point B, you could just make it a straight line from point A to point B, and you'll get the same value for the integral. Or you can use the fundamental theorem of line integrals. So you have options for your FDR problems. All right, and then today you're going to learn options if your vector field is not conservative. So we've got options, easy options if the vector field is conservative, and then after today we'll learn options if the vector field is not conservative. But before we do that, let's just practice real quick. So I want you to find the line integral of f dot dr, where the vector field is y cubed plus 1 for the x component and 3xy squared plus 1 for the y component. C is the semicircular path given by that r of t, 1 minus cosine t in the x component and sine t for the y component, from 0, 0 to 2, 0. So the first thing I personally would check would be to see if f is conservative. Because if f is conservative, then you can do this using either changing your path or doing FTLI. If f is not conservative, then you got to do the old-fashioned way. So take a minute. I'm going to walk you through, just for the video's sake, I'm going to walk you through the three possible ways you can do this problem. So way number one is to go ahead and just do f dot r prime, right? If you go ahead and just do f dot r prime, then you have to rewrite your f where, like, if this is your x and this is your y, right, you'd have to replace this. So this would be sine cubed plus 1, and this would be 3 times this squared plus 1. And then you would do the dot product of this vector and this vector, right, and then integrate that. You could do that. It is a lot of work, yes. So that's method number one. Method number two, did anyone test to see if big F was conservative?
Yes.
Is it conservative?
Yes.
Yes. Since big F is conservative, you have two options. One is you can change your path, right? So currently we're following this r of t to get from 0, 0 to 2, 0, but we could just as easily follow r of t equals t comma 0 from 0 to 2 and do the exact same problem f dot r prime, which would be much, much easier, right? So you could do that, or you could use the fundamental theorem of line integrals. I personally like the fundamental theorem of line integrals the best. So first you have to find your potential function, right? So Do you guys need me to walk you? I'm happy to walk you through. Do you want me to walk you through finding the potential? Yes? Okay. All right. So potential function for f. So our little f. So you integrate y cubed plus 1 with respect to x. So I'm going to put like this little x here. So we have xy cubed plus x. And then you do the same thing with your y part. I'm not writing good notation, but that's okay. So you do the same thing with your y part. You integrate the second part with respect to y, and you get xy cubed plus y. And then when you write your potential, it's all of these terms but without repeats. So you have an xy cubed plus an x plus a y plus k for your unknown constant. Okay, so there's your potential function. And then all that the fundamental theorem of line integrals says is that the integral of f dot dr is equal to the potential function evaluated from beginning point to end point. So you plug your end point in, minus plug your beginning point in, and you get your answer and you're done. Right? Yes?
So you made your R thing. Like the RT equals T like 0, comma 0. So are you serious about making your own RT and what follows the path?
So this was me doing it using the RT T comma 0, and I actually worked it out both ways so you could see that it actually works both ways. It's really, like when you change your RT, look at how easy the integral becomes, right? So this way is really no harder than FTLI. It makes it really nice. So as long as the vector field is conservative, you can get from point A to point B on any path you want, as long as it's a path that works. And you'll have an equivalent answer. All right, any questions on that one? Tejas, do you have a question? No? You sure?
Yeah.
All right. Okay, so that's it for this lesson. That was all we needed to do to finish off fundamental theorem of line integrals. Now we're going to switch to Green's theorem. And I do have a warm-up. And I think I want us to take about 5 or 10 minutes and do the warm-up because it's a good review. So your first question, find the area of the lateral surface. This is not a work problem, so you are going to just have to do this using a traditional line integral. It's my way of forcing you to find an old-fashioned one, right? So find the area of the lateral surface if your f of xy is x squared minus y squared plus 4 over the curve x squared plus y squared equals 4. So you're just following along a circle with that as your height, right? Okay. Part 2, find the work done by big F of xy. Make sure you check to see if it's conservative. And part 3, evaluate f dot dr if f equals that. Again, I would check to see if it's conservative. It might be, it might not be. So if it's not, then this could be my way of forcing you to have to find parametric functions for these 3 lines. Yes, so the arrows look like that, that, that. All right. All right, I'm going to have a lot of good discussion on this problem. I enjoyed walking through this with quite a few of you. So find the area of the lateral surface of f of xy equals x squared minus y squared plus 4 over the function c. Hint, this would be a good one for polar. So I let x equal r cosine theta, r sine theta, and since our r is 2, you get 2 cosine theta and 2 sine theta. So then you have to rewrite your f in terms of theta, and you have to multiply it by the arc length of r, right? So you end up with square root of 4 cosine squared plus 4 sine squared, which is root 4, which is 2, and you can pull out a 4 out of each of those and put an 8 out front. But anyway, so you end up with that, and then I pulled out an 8. Okay, this is where some people got stuck. I would rewrite cosine squared minus sine squared as cosine 2 theta. Some of you just did power reduction on both of them. If you do power reduction on both of them and combine like terms, you still end up with cosine 2 theta. So no matter how you do it, you end up with a cosine 2 theta, and then the antiderivative of cosine 2 theta is 1/2 sine 2 theta, and the antiderivative of 1 is theta. And then you plug in your 2 pi, minus plug in your 0, and you end up with 16 pi. Somehow I think your coefficient right at the beginning, 4 times 2, you know what? You have 4√4 on this step, and the very next, this right here. Oh no, that was because of your halves. You know what? I found it. This is equal to 1/2 times 1 minus cosine 2 theta. This is equal to 1/2 times 1 minus 1 plus cosine 2, whatever. Okay, you get it. 1 divided by a half is not a half, it's 2. So this should have been 2, 2, 2, 2, and that's where the problem is. Yeah. So, little mistake. All right, good. Almost everybody figured that out eventually, which is really good. Are there any questions on, look at this, look at all those beautiful 16 pi's. All right, the next one, if you check, it is conservative, so I would have probably just done this with FTLI, and yes, yes, yes. It's a lot of work for just, okay, and I got negative 17/4, negative 17/4. I see a negative 17/4, I see a negative 17/4. I see a negative 17/4, like with big banners around it. And yes, we all got number 2. So we all love fundamental theorem of line integrals, right? Who doesn't love FTLI? All right, the last one, you had to rewrite your equations in parametric form. So I did each curve separately. So I did T0 for my first curve, probably from 0 to 3, yep. And then I did my second curve, which was 3 comma T from, would have been what, 0 to 3 again. And then I did my third curve, which was TT. And I did it from 3 to 0. I like was lame. So you could do that. It's the same as doing negative T. It's the same thing as reversing it and making it negative T, negative T. But anyway, or 1 minus T, 1 minus T, or 3 minus T, 3 minus T. Yes? Are you okay? Okay. All right. So that's enough of that. So we're going to move forward, and today we're learning Green's theorem. 15. I forgot to change again. I swear to you, I did go through these. I just keep forgetting this little title thing. So anyway, there we go. 16.4. Green's theorem. All right, everyone ready? 16.4 Green's theorem. Sai, you ready? All right. If R is a simply connected region with a piecewise smooth boundary C oriented counterclockwise, and if M and N have continuous partial derivatives in an open region containing R, then the line integral of M dx plus N dy is equal to the double integral of partial N partial x minus partial M partial y over the area of the region. It's really actually not that bad. Okay, so here's the thing. So Green's theorem, again, allows us to evaluate line integrals without having to convert to parametric form. Note, Green's theorem only works if the vector field is not conservative. Because if the vector field is conservative, what would this equal? 0. Right? Okay. It's this right here. The integrand for Green's theorem is the exact same as your test for conservative. All right. Okay. A simply connected region is a region basically with a boundary that doesn't cross over itself and doesn't have any gaps. So it's a region where you can draw the boundary without lifting your pencil and it never crosses over itself. So nice, simply connected region. No holes inside, no crossovers. So Green's theorem only works in 2 dimensions. Stokes' theorem is basically Green's theorem in 3 dimensions. So we're going to be doing, when we get to Stokes, it's the same thing, just with 3D. So, anyway, Green's theorem only works in 2 dimensions. So we're going to actually go back. We're not going to talk about curl. I saw that. I thought about taking that, and I just left it. Okay, so, sure. Don't forget, on the last set of slides, we already pointed out that the line integral over some curve C of m dx plus n dy is equivalent to f dot dr. So now we know that that is also equivalent to partial n partial x minus partial n partial y dA. So we're actually going to get back in the habit for today of writing double integrals that produce an area of a region. Okay. A lot of writing. Tell me if it's okay for me to scroll. You're done? Okay. All right. Can you use the theorem when the path is oriented clockwise? Why does the path have to be oriented counterclockwise? Oriented counterclockwise, the way that they talk about this, a lot of mathematicians talk about this. I don't know if your book says it like this or not, but like say this is our curve C, right? Has to be simply connected. Has to be a closed region, like it's all enclosed, right? So if we have some simply connected path, that means that if we were to walk along the path, the region that's enclosed would always be on our left. So when they say it's a counterclockwise oriented region, that's what they mean, is if you're walking along the boundary, the region, the stuff is always on your left. Now, I have a student who actually asked the question, can't we do it? I mean, would the math be that different if it was clockwise oriented instead of counterclockwise oriented? No, you'd actually get the exact same answer, just negative. So if you have a clockwise oriented path, you're going to end up, you get the exact same answer, just times -1, and that's okay. Just know that if you want to answer the question, remember that this integral is actually giving you work of a path of an object traveling through a vector field. So since we're actually calculating a value of work, the sign's kind of important. So if your path is oriented counterclockwise, you get this theorem will give you the work. If it's oriented clockwise, then you got to multiply your answer by -1. That's all. Okay. How what? They have to give you a picture of what's going on or tell you. Okay. All right. Okay. So I've retyped Green's theorem right there. All right. So we're going to use Green's theorem to evaluate the integral over the curve C of y cubed dx plus x cubed plus 3y squared dy. C is the path from 0, 0 to 1, 1. along y equals x cubed, and 1, 1 to 0, 0 along graph of y equals x. Personally, I would start by sketching my, I don't have my sketch though. All right, so we're going to move this over and draw a sketch. All right. So 0, 0 to 1, 1 along y equals x cubed, and then 1, 1 to 0, 0 along y equals x, not drawn to scale. So here's 1, 1. Here's 0, 0. This is y equals x cubed. This is y equals x. Rather than having to figure out this path in parametric form, which really wouldn't be that hard, but rather than having to figure it out, and remember we're going this way, 0, 0 to 1, 1 along the x cubed, and then this way, 1, 1 to 0, 0 along y equals x. We are counterclockwise oriented on a simple connected region, right? Okay, so rather than sitting there and converting these to parametric and converting that also to parametric and then doing an f dot dr, instead we can apply Green's theorem over the double integral that gives us the area of this region. So the double integral that gives us the area of this region, I personally would just do a dy dx where my x goes from 0 to 1 and my y goes from x cubed to x, right? Top minus bottom. Easy peasy, right? All right. So, oh, but we got to do, oh, that's just me setting it up. All right. So to set up the integrand, so you have to do dn dx plus, or minus dn, I can never say this right, dn dx minus dm dy. So if you want to go ahead and take a minute and find like the guts of your integrand, your Green's part. So partial n partial x minus partial m partial y. This would be, this is like your m, and this is your n. Yes. So don't look at this part, but let's hear. For the Green's part then, partial n partial x would be 3x squared plus 3y squared. And then partial m partial y would be 3y squared. So you have 3x squared plus 3y squared minus 3y squared. And then dy dx. And then your limits of your integrand are the limits that give you the area of that region. Which now, whenever we have a region of this shape in AP Calc, I'm calling it a banana region. So, the area of the banana. Set up your double integral. So you should have x going from 0 to 1 and y going from x cubed to x. Then clean up your integrand and go ahead and evaluate. It would be like a breath of fresh air to do a simple dy dx integral. Danny, you okay? Do you understand why it's x cubed to x? You want to do dx dy, you got to solve these for x and have them determine. So could we be doing a right minus left kind of thing? Because then you're using the y have to be numbers, so the x is having to be on the y. So you would have to do root y minus y, root y to y, right to left, and then 0 to 1, 3 y. Yeah. You have to convert. Okay. All right. Good. So, this is me just reiterating again that this is equal to f dot dr. So again, this gives even Green's theorem gives the work done on a particle moving along path r through vector field f. That's just me saying that again. Okay. All right. Use Green's theorem to calculate the work done by the force F, big F of xy equals y cubed x cubed plus 3xy squared on a particle traveling once around a circle, I almost said circus, around a circle of radius 3 centered at the origin. Centered at the origin. So your path notice it didn't say traveling counterclockwise. Let's make it counterclockwise. Circle of radius 3, centered at the origin. So there's your path. Remember Green's theorem? You just need the like it's the double integral over the area. If you want to keep this with x's and y's, that's fine. If you want to convert it to polar, that's fine. So whatever you prefer. But you might want to do your how do I say this? dn dx minus dm dy first, and then do a polar conversion if you want to convert to polar. So I just tried for the heck of it to do this problem without converting to polar, and it can be done, but it requires a lot of trig substitution, right? Okay, so much easier if you convert to polar. So we have 3x squared evaluated over the integral. So this is the integral as r just goes from 0 to, why did I not do my limits right away? R goes from 0 to 3, theta goes from 0 to 2 pi, and remember it's x is r cosine theta times r dr d theta, right? So I just cleaned that up and then apparently waited 4 steps to put my limits on. So there we go. All right. So and I differentiate dr. So 3/4 over the 4th. Plug in, you get this guy. Antiderivative of cosine squared. You have to do a power reduction. So you end up with 1/2 times 1 plus cosine 2 theta. And we antidifferentiate cosine 2 theta. Antiderivative is 1/2 sine 2 theta. So you end up with 243 pi. Is that what you got? Okay. Did you? Yay! You messed up twice, but you got it?
Oh, yeah.
Okay. All right. The main part that I want to make sure you learn is the setup, right? So, do you understand how to convert from the F, the big vector field, to apply Green's theorem? And then setting up area is what we did last chapter. So, I'm not worried about that. Most of you can do an area just fine. Here's another one just for fun. So evaluate f dot dr if your vector field is e to the x. I thought it'd be good to put some e's in. E to the x minus 3y, comma, e to the y plus 6x. If your r, your path, is 2 cosine theta. Why do I not have any limits?
Maybe you just need to scroll down.
Do you think there's more? No. There's the Green's theorem. I think I just have, it looks like I just intended for you guys to do it from pi halves to 3 pi halves, but I'm not sure. Oh, this is a polar equation. This isn't y equals cosine 2 cosine x. This is r equals 2 cosine theta. This is already in polar form. It's already defined for you in polar form. So we have a lovely polar equation, r equals 2 cosine theta. So see if you can write your Green's theorem setup and see if you can graph this in polar form. Find your limits. Right? You can do this. At least do the setup. You don't have to evaluate. Do the setup. So do you guys remember 2 cosine theta? If when in doubt, plot points, right? That's what my geometry teacher always used to say.
Wait, is the circle like
No, you can point. It's okay.
circle above the like that?
Is it above or is it next to it? Plug in. At when theta is 0, which is here, right? What's your radius? 2. Okay. When theta is pi halves, which is up here, what's your radius? 0, right? See if you can plot a few points and figure out where it is. It won't? Oh, you probably have to you have to re-download it. Okay. So did it give you an option to because you have to, when you go 0 to 2 pi won't work because you'll double your 0 to pi. Sorry. Yes, 0 to pi should work. You're just going top to top instead of side to side, or out to out. That's fine.
Thank you.
So anyway, your radius 0 to 2 cosine theta, and then your thetas. So what I didn't get on the recording that I'll put on right now is I'll put this over here. That's 1. That's 2. You set 2 cosine theta equal to 0. Cosine theta equals 0. Find 2 consecutive angles. I did pi halves to 3 pi halves, but any 2 consecutives will work. Okay, the main thing I'm concerned about is the setup. Talk to me if you have questions, even though the bell rang. Have a great day. You guys over questions?